Section 3, bacterial viruses. Turns out, not only do humans get viruses like this Spanish influenza and catch a cold, but bacteria get viruses too. Turns out bacteria deal with viruses. There are, and people found at this part of the century, these strange things that attached to bacterial cells and would kill them. And these were viruses. I've drawn this way out of scale here because I've made the virus too big compared to this cell. The cell is much larger than this, but I wouldn't be able to draw you a good picture here and for you to see it. These viruses could be added to a mixture of bacteria. They would attach to the bacteria, and in some number of minutes, 20 minutes, 30 minutes, they would destroy the bacteria. They would kind of eat up the bacteria. They were referred to, because they could kind of, they thought eat bacteria, as bacteriophage. Phage means to eat. So bacteria eaters, bacteriophage. In fact, there were people who had all sorts of ideas in the early part of the 20th century that maybe this was a good way to cure you of a bacterial infection, was have you drink a lot of bacterial viruses so that your bacteria would get sick with viruses. That hasn't really worked out, but it actually got people interested. The point was these viruses, when they killed the bacteria, didn't just cause the bacteria to die, it caused the bacteria to burst open, and lots and lots and lots of bacterial viruses, bacteriophage, would burst out. It would replicate and make thousands of copies of itself. It sort of might be thought of as a living organism. Now, as a living organism, I suppose you could call it, people love to debate as a virus, but living or non-living, I don't really care. The point was, a virus, when it goes into a cell, can replicate itself. It needs the cell to replicate itself. So replication goes on. For that, in that sense, this is a replicating thing, and it's very simple. And it clearly somehow has the instructions to make more of itself. It has some sort of heredity to it. It's able to make progeny, offspring. But it's very simple, much simpler than a cell. In fact, it was so simple because all it really had was it had an exterior package, a capsid that was made out of protein. And inside that capsid, it had DNA. There are really only two choices for what could possibly be carrying the heredity here. It was either the protein or it was the DNA. And all you had to do was find out which it was. So, two people, Al Hershey and Martha Chase, did what are known, not surprisingly, as the Hershey-Chase experiment. They took bacterial viruses, they let them attach to the bacteria, and they asked what went into the cell. Was it protein that went into the cell or the DNA that went into the cell? If it was the DNA that went into the cell, it must be the DNA that's carrying the instructions. How could they tell? How would you know whether it was the DNA that went in or the protein that went in? You'd have to
use biochemistry to separate them and inject each individual.
I could use biochemistry to purify the protein component and the DNA component, and then how do I get them into the cell? See, the virus is this insidious device that can inject whatever it needs to into the cell. It's a living, working mechanism. The minute you grind this thing up to separate the protein and the DNA, it now doesn't actually work. So how am I going to get into the cell? It's an idea. We could purify and try each component, but I don't know how to make it work then. It's broken. What else can I do? Yes?
Add fluorescence to either just protein or just...
Ooh, if I could fluorescently tag just the protein and see if the fluorescent label goes in, or fluorescently tag the DNA and see if it goes in. how do I fluorescently tag something? Gonna need some fancy chemistry to take this virus and sort of chemically attach a fluorescent chemical group to the DNA and then stuff it back in the head of the virus. It's a great idea, but I don't know how to do that. But but you've proposed a label. You've said label it somehow. How else could we label it? Radioactivity. Ooh, if I had a radioactive element that only went into proteins, but not into DNA, then I would have labeled the proteins. Now I have to think of some atom that is found in proteins and not DNA. Yes? Sulfur. Bingo. All right, so we want to label, this is great, guys. We are creating this experiment. We want to label the proteins one way and the DNA another way. And we're going to use a radioactive element. Now, actually, how do I make radioactive protein? Do I go in there and I install little, radioactive sulfur into my protein? How am I going to make viruses that have radioactive sulfur in their proteins? Any ideas? Yep.
You just make the virus replicate in the presence of radioactive sulfur. As
Bingo,
opposed to
that's it.
sulfur?
All I need to do is I throw in, maybe I'll make it, radioactively labeled cysteine or sulfur in some form that can be taken. I just grow it in the presence of radioactive sulfur, and when it replicates, it has radioactive sulfur in it. It turns out to be a piece of cake. No problem. So you want me to label this with sulfur, and S35 is the isotope I'm going to use because proteins have sulfur. What amino acids have sulfur? Cysteine has sulfur, and sorry? Anybody else have a sulfur? Methionine, maybe? Yes, methionine. Excellent. So there's two amino acids that have sulfurs in them. And DNA has no sulfur because I didn't show you any sulfur here in the DNA. What does DNA have, though, that I can use? How about nitrogen? Poor choice, because proteins have nitrogen. Oxygen, poor choice. Phosphorus. Proteins did not have any phosphorus when we put up those amino acids. So I can use radioactive P32. P32. Radioactive phosphorus, radioactive sulfur, bingo. If I grow the virus in the presence of radioactive sulfur or radioactive phosphorus or both, I get a labeled virus. I now take a tube of cells. Here's my bacterial cells. I'm going to add virus to it. And the viruses floating around here are going to attach and inject something into those cells. And I need to know what goes in the cells. And I can do that by figuring out which radioactive label goes into those cells. Now we have a problem. The virus is attached to the outside of the cell. I want to see what's inside the cell. I don't want the virus attached anymore. I have to dislodge the virus from the cell. Otherwise, I'm not going to be able to tell what's inside versus what's outside because they're stuck together. I need some incredibly powerful device to create shear forces at the molecular scale here, shear forces at the viral scale here that are going to knock this virus off. So you need some pretty fancy technology to knock off these viruses to create violent forces. And I brought it here. It is the kitchen blender. In fact, the Waring blender. These are called the Waring blender experiments as well. And you would put them in. And you would press puree. And the violent forces there would then knock the viruses off the cells. They would go floating around. And now I need to separate them And it turns out that I can do that by centrifuging the mixture. The denser bacteria go to the bottom, the lighter viruses stay up in the supernatant. I pour off the supernatant, and I see which radioactive element went in and which goes in. Phosphorus. Bingo. It's the phosphorus. So when I do this, and I do the blender, and then I centrifuge, so the blender separates the bacterial cells here from the little viruses. And when I centrifuge the bacteria pellet at the bottom, and my little viruses are up here, and I measure it, and what goes in here is P32, definitively proving that the heredity is due to DNA. Because absolutely no sulfur is found down there at the bottom. Do you believe that? Do you believe that 0 radioactive sulfur in any experiment you do in the lab is found down there at the bottom? That we've managed to perfectly get all that virus? No, of course not. There's about 1% of the radioactive sulfur still there. So suppose you were a churlish biochemist. What would you say? There's still a little bit of protein there, and it's doing it. But, you know, time's moved on here. We now have 2 different ways to think about it. We got this bacterial virus experiment, it's mostly giving us this answer. We got that pneumococcus experiment, it's mostly giving us this answer. It's beginning to make sense. And also the people who are doing genetics were studying a lot of these bacterial phages and liked them a lot and kind of believed it. And the combination of Avery's experiment, which was well known by now, and the Hershey-Chase experiments pretty much said, it's got to be the DNA. Pretty amazing story so far, but stop for a moment and test yourself with this question about the Hershey-Chase experiment.